Now, there's one particular analogy that is especially enlightening, and that is the analogy for translational kinetic energy. So let's just say we have a disk here, a large disk, and it's massless. So I don't have to worry about the mass of this disk. It's got a large disk, and on this disk I have two different masses. Here's the axis of rotation of the disk, which I often make as a star, like that, an asterisk for the axis of rotation. And what I have is I've got here's mass 1, just say it's a point mass M1, and its distance from the axis of rotation is R1. And this is important because this R has different meanings depending on what you're talking about. And I'm going to help define that for you with a little rhyme here. Let me just put in R2 and mass 2. So we have another mass. Maybe it's a little bit bigger, or it's still a point mass, but it's got a greater magnitude. R is, and I made a little rhyme for this to help you remember it, R is the displacement from the axis of rotation to the point where the mass is stationed. This is really important because this is the definition of R for moments of inertia and for angular momentum. R is the displacement from the axis of rotation to the point where mass is stationed. So here's the axis of rotation, here's the point where the mass is stationed, that's R2. Here's the axis of rotation, here's the point where the mass is stationed, R1. And this, we can just say that this thing is rotating this way. Rotating this way. Okay, so that's omega is counterclockwise. Now, let's see if we can derive an expression for the kinetic energy here in terms of some rotational variables. Now, it will make sense that what is the kinetic energy? The kinetic energy of the system, the net kinetic energy over all I, capital K, is equal to the sum of 1/2 mi vi squared, right? That is just simply the kinetic energy of M1, the kinetic energy of M2. So it's 1/2 M1 V1 squared plus 1/2 M2 V2 squared. Now, I'm doing this for a system of two objects on a massless disk. This can also be true for a system of infinite, really tiny objects. In fact, that's what we have to do when we're finding the moment of inertia of a solid object. You have to do this same thing. We have to add up an infinite number of these. Physics 1 and 2 people do not have to do that. Physics C people do. We're going to have to do some integrating to add an infinite number of things. 1/2 M1 V1 squared plus 1/2 M2 V2 squared, the total kinetic energy of these. There's another way to express that in terms of angular variables. Let me just draw on here. This is the instantaneous V1 of that thing. This will be the instantaneous, and it's a shorter value, V2 of M2. This is all equal to the sum of 1/2 mi. Instead of vi, I'm going to express this in rotational variables. That would be ri times omega. Notice omega is the same for both objects, squared. And all I did, this is just vi right there. Let's rewrite this. That's the sum of 1/2 mi ri squared omega squared. And then I can rewrite that as follows. This will equal the K, the net kinetic energy, equals the sum of 1/2 mi/ri squared. I'm going to put that together. And I've done nothing but just put this together. But what I'm going to do is I'm going to call this thing right here I, the moment of inertia of this system. And that gives us, we can express this rotational kinetic energy, as, notice how this analogy works. If I call this I, this is simply the sum of 1/2 I of the moment of inertia of the ith object times omega squared. Notice how this is just like 1/2 mv squared, but these are rotational analogy variables. These are rotational variables. So if I just call this thing MIRI, like the mass 1 R1 squared, that would be the moment of inertia of object 1. Mass 2 R2 squared, that would be the moment of inertia of object 2. It's important you understand what this R is. R is the distance between the axis of rotation and the point where the mass is stationed. So you can express the kinetic energy as this, or you can express the kinetic energy, and I'll rewrite this. You could do it like this: 1/2 I1 omega squared plus 1/2 I2 omega squared. Now notice that the omega is the same for both of these because they're on the same massless spinning disk. So here's what this means. If I just define I, the moment of inertia, as the sum of all the mi's times their respective ri's squared, then the analogy works perfectly. Now, if we have a solid, this only works for discrete masses that are spinning around on like a massless disk like this. For a solid object, it becomes this. We have to use calculus. We're going to add up an infinite number of little teeny masses. So we express it like this: r squared dm. And it's the same thing as up here, but it's for, instead of mi, it's little tiny dm's, little pieces of mass. And instead of the ri squared, it's each respective radius. They're each little infinitesimal masses displacement from the axis of rotation to where the mass is stationed. That's what r is for each one of these. And we have to add up an infinite number of those. And we'll see how to do that in detail later. Now, I do need to mention at this point that if you're talking about discrete masses, that means like individual masses like m1 and m2, you have to use either k equals 1/2 mv squared or k equals 1/2 I omega squared. You can't double count it. Kinetic energy is kinetic energy. Although we often label this k translational and k rotational, it's all the same stuff. It's all made of joules. There's no real distinction between one kind of kinetic energy and another. We just like to sometimes put these subscripts on there to remind us of which motion we're talking about. For these masses, you can just look at them. Okay, they're moving instantaneously in a straight line at speed v1 and v2. So you could add 1/2 m1 v1 squared plus 1/2 m2 v2 squared and get the kinetic energy of them. Or, not both, but or, you could calculate the moment of inertia of each one, which would be mr squared. For this one would be m1 r1 squared. For this one would be m2 r squared. And then multiply that by omega squared and add up that. But you can't double count it. Now, it is true that for solid rotating objects, there can be both. For example, here is my circular object right here. If this was rolling, for example, this could have rotational kinetic energy and translational kinetic energy. You can have both of those because it's not only moving rotationally, the center of mass of it can be moving translationally as well. So when you have a solid object that's moving translationally, you have to count both. The net kinetic energy for a solid object like that would be 1/2 its mass times the velocity of its center of mass squared plus 1/2 its moment of inertia times its angular velocity squared. You have to count both of those for a solid object that's rotating and moving translationally.